These notes are going to be on topic 2, kinematics. Before I begin, topic 2 is technically called mechanics, and there are about 6 different units that will be encompassed underneath topic 2. So I broke it down into kind of like the general topics or chapters that you would see in a general physics course. Inside kinematics, I'm going to take it one step further and break it down into 1D motion, where you're only utilizing one axis at a time, versus 2D motion, where you're utilizing 2 axes simultaneously. That's when you would have to start using the trig stuff. That's when the sine of theta and cosine of theta and tangent theta will come into play. So to begin here, topic 2 on kinematics, we're going to look at 1D motion, in which motion is one-dimensional motion as the simplest form. So if there would be a multiple choice question, which form of motion is known as the simplest form of motion, you would say one-dimensional motion. I'm going to refer to this as 1D motion. For instance, an object that moves forward and backward only, or left and right only. It is never a combination of more than one axis simultaneously when displaying 1D motion. So once again, you're only utilizing the x-axis. You're only utilizing the y-axis. That would be 1D motion. So for instance, here we have a picture of the subway, in which the subway is traveling north, and then it comes back to travel south. And it travels north, and it travels south. So it's 1D motion. Okay. Also, motion takes place over time, so we're going to draw out different graphs. This example here for number 3 is a position time graph. The other word for position is displacement. So if you see the word position, go ahead and think displacement. Also, it's going to depend, motion, it's going to depend on a frame of reference. This is really, really important. Your frame of reference is going to be a stationary point. So for instance, it says a system of specifying the precise location of objects in space and time. In order to figure out exactly where something is in space and time, one object has to be at rest. Agreed? So look at this picture here. There's a tree and a car is coming towards the tree, and a car is going past the tree. So therefore, the tree is your frame of reference. So like to say an airport, for instance, would be a frame of reference. How far are you traveling from destination A to destination B? How much longer is it going to take you with a layover at this stop? Because those things are stationary. So if you would have 2 things that are moving, then you would have to talk about relative motion or relative velocity, because it's relative to me. Well, your relativeness may not be the same as someone else's. So let's first talk about displacement. What I'd like you to jot down here is that this is a change in position of an object. The equation that I would like you to learn for this, very, 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 very basic, is delta x, where delta means change in, final displacement minus initial displacement. And that should make sense, right? Because change in means take the difference between. Taking the difference between means that you are subtracting things. So x sub f would be your final displacement. Measured in meters. Meters is like the fail-safe unit that you want to go to. xi is your initial displacement, measured in meters. Remember, once again, they have to be the same in order for you to calculate what the change in. So change in displacement. Which will be measured in meters. Remember to apply the correct sign. When we say correct sign, we mean show direction. So very, very basically, if you have a positive displacement, then you're either moving up, right, north, or east. If you have a negative displacement, you're either moving down, left, south, or west. This was taken from the Holt General Physics textbook. I just copy-pasted this into here, kind of showing you some different examples of if an object is moving towards the right, then you are taking your final minus your initial, you should come up with a positive displacement. But if an object is moving towards the left, which would be the right-hand side of the chart here, then you would have a negative displacement because you're still doing final minus initial. So you're taking like a negative 20 minus a negative 80 or whatever. So it's going to give you a very big difference there. Okay, so let's try this. Look at this gecko here. Let's say that this gecko is moving in meters, guys. So it took a very long time for it to move from position A, initial displacement, to final one. But what I really want to do here is assess the idea of guess. So follow along with me here. Go ahead and talk out loud. This says that you have an initial given of a displacement. What is your initial displacement here? Well, let's keep the math simple and say 25 meters. What is your final displacement? Let's come over here and look at this. Oh, 85 meters. So that's your G in guess. Your U stands for your unknown. So what are you trying to solve for? The change in. What units will this guy be measured in? Meters. You do not need to convert any of the units because everything is in meters. That looks great. So let's move on to E. And technically, this is called the original equation, not just the equation. So the original equation comes from your notes, directly from your notes. So the only one that I gave you is delta x equals x sub f minus x sub I. We don't need to rearrange this whatsoever. So we're at that first S now where we just simply substitute in. Your final is 85 and your initial is 25. So that gives you a difference of, do it in your head real quick, guys. 85 minus 25 gives you 60. So that gives you a delta x. Now you're at your final S, which is solve through with correct units and sig figs. Looking back over here at your givens, you have 2 sig figs. So your final answer needs 2 sig figs. Well, looking at the number 60, there's no decimal there. Therefore, technically, there's only 1 sig fig. So we really want to write 6.0 times 10 to the first meters. That is our change in displacement. In other words, 60 meters. We just want to hold through on sig figs. So this is an overview of how you're going to use the guess method. Please apply this to every single problem you're going to do with me, especially those worksheets that are for homework, any other types of problems where you have to show work. Utilize the guess method, please. Okay, speed versus velocity. This is going to be a little conversation on scalar quantities versus vector quantities. For scalar quantities, we are talking about magnitude only. So you're not telling me the direction that you are traveling in. Whereas with vector quantities, you're telling me the magnitude, but you're also telling me the direction. So you're going to see positives and negatives written in front of the numerical value that's assessed with the units that accompany it. Okay, so with that in mind, excuse me, let's look at these examples. It says, which of the following shows speed and which one shows velocity? Well, let's look for the speed one first. It says, I traveled here at a rate of 16 meters per second, or I traveled from the north at a rate of 16 meters per second. Well, speed, if you look above, is an example of a scalar quantity. Okay, so you want to find the one that shows magnitude only, one that is not implying direction. So let's read them one more time. I traveled here at a rate of 16 meters per second versus I traveled from the north at a rate of 16 meters per second. Well, the first one here is going to show you speed because it does not give you a direction, whereas velocity is going to be a vector quantity because it is going to show you a direction with the magnitude. So this last one is an example of velocity. Average velocity. For average velocity, please write this definition down. Total displacement divided by the time interval during which the displacement occurred. Total displacement divided by the time interval during which the displacement occurred. Your equation here is going to be the average equals delta x over delta t. Or you may just see it very generally written as velocity equals displacement over time. Your variable is here, and I'm going to stick with the general, guys, because I know that you understand what delta means. So x is going to imply displacement, and displacement should be measured in meters, and t is going to stand for time, and that should be measured in seconds. So therefore, what will velocity's units be? Well, look at the equation. If you have velocity equals displacement, which is meters, divided by time, which is seconds, then your units for velocity should be meters per second. Cool. All right, so there's some equations that you need to learn. Graphing average velocity. Known position of an object at a specific time along its path. So you're going to have a position time graph. So the first thing I would like you to do is title this graph. Don't lose the easy points. Remember your titles, remember labeling your axes, be consistent with your increments, etc., etc. So position versus time. Now, follow along with me here. This should be review. Which variable is on your y-axis? Say it out loud right now. Which variable is on your y-axis? Position. Which variable is on your x-axis? Check the graph out. Which one's on the x-axis? Time. Okay, so position versus time, what you're going to be looking at then is figuring out what the slope is representing. Well, to figure out the slope, guys, what's the very, very basic math equation that you want to use? Think about it, like m equals what, guys? So that would be delta y over delta x. So in this case, it's going to be position divided by time. In other words, that is displacement, sorry, let me try that again. This is going to be displacement divided by time, which is meters over seconds, which is velocity. So the slope of this graph is telling you velocity. And how did you know that? Assess the units. Your y-axis unit divided by your x-axis unit. That will tell you what your variable's slope will be. Let's look at this graph real quick. So this one you're showing three different objects. One object is clearly standing still as the gun goes off, like you're running a race. So as time is going on, you are just standing still. This person, as time was going on, they ran away in the positive direction. And this person ran away in the negative direction. Make sense? So what then you want to look at is the slope, the steepness of the slope. Look how number one is steeper, therefore traveling faster than this one right here. So it's traveling fast, we'll say, but not faster. And then obviously the red one is at rest. Don't say standing still. At rest is the physics terms that you want to say about that. What should you add to make this a very thorough, completely identified graph? What's missing? You got your labels over here, meters and seconds, but most importantly, don't forget to add that title, always, always. Y-axis versus x-axis. So title this graph, please. Position versus time. Very good, guys. Recapping here, look at the steepness of a slope. The steeper the slope, the faster the object is moving. Now, I'm being very specific and talking about position time graphs. If you see an object that makes a quote-unquote flat line, then you are experiencing an object that is at rest as time goes on. So we're going to start with the next video here on talking about instantaneous velocity and doing a sample problem. So jump on to the second half of this video at this time, please.